Let's investigate some properties of the density operator. We're going to be using the trace. So let's begin by taking the trace of an outer product constructed from the ket psi and the bra phi. So this is a ket-bra combination, which is an outer product in Dirac notation. And we're going to take the trace of this object. That can be expressed as the sum over some index n, and then we're going to sandwich this ket-bra combination in between bras and kets of these n's. So we'll have bras coming from the left, and then we'll have psi and phi in the ket-bra combination, and then we'll have kets coming in from the right. So this is a bra-ket sandwich of the object we're taking the trace of. And now we can identify that this is the outer product, the ket-bra in the middle, but we can also identify that we have two inner products. Here is an inner product, and here's another inner product. And those inner products will be evaluated as complex numbers. So we have two complex numbers that satisfy commutativity. Now we can swap the order, and that's going to give us the sum over n of, first we need to put this phi, so we have phi, and then a ket-bra of n's in the middle, so that's this part over here attaching to this part, and then finally we have psi. And this is the same as the identity operator. This is actually called the resolution of the identity. So we can identify that this is the identity operator in between phi and psi. So we can ignore it because the identity operator has no effect. So that means that this is the same as the inner product of phi with psi. So in this example, we have used the trace to turn an outer product into an inner product. So this is very convenient in Dirac notation. And the point of this example is to illustrate how we can express the trace in terms of some basis, and how we can express the identity operator in terms of some basis. And this basis is labeled by the index n. So these n's are just labels for some basis that we're using to compute the trace, and we're using to construct the identity operator. And notice that the identity operator is constructed by these projectors. And then we have to sum over all of those projectors, and that gives us the identity. So this is a very useful property. Now let's use the trace and this identity operator to discover some interesting properties about the density operator. First, let's begin by analyzing the expectation value of an operator in quantum mechanics. So let's say we have some arbitrary operator, let's call it A. The expectation value is denoted by A in these triangular brackets over here. And we can write this expectation value as the sum over some index k of probabilities, pk, times the bra-ket sandwiches of A between states psi k. So I'll write that out. We have psi k as a bra, then we have A, and then we have psi k as a ket. So this is a bra and a ket, and we're making a sandwich of this operator. So if we were dealing with a pure state, then we would only have one value for this index k, and pk would be equal to 1. So then we wouldn't have to consider this summation. We would just be taking the sandwich of the operator between these bras and kets for the particular state that we've prepared the system in. But if we were dealing with a more general case of a mixed state, then we have to do this linear combination with probabilities as the coefficients in the linear combination. So each of these, you can think of them as terms in a weighted average. And this weighted average has these probabilities as the weights. And this gives us an expectation value. So this expectation value is something that we can experimentally verify. So this works for these arbitrary operators in quantum mechanics that correspond to physical observables. Some examples would be the Hamiltonian operator. And if we put the Hamiltonian operator here, we would get the expectation value of the Hamiltonian. And that's associated with the energy of the system. We could also put momentum over here. That's linear momentum. Or we could put angular momentum. And we can also put position. These are observable quantities in quantum mechanics. And they are described by these operators. And specifically, they're Hermitian operators. And that means that the eigenvalues are real numbers. And that is very useful because when we're doing a measurement, we are measuring real numbers. So let's express this using this identity operator. So we can insert the identity on the right-hand side of this operator A. So I'll do that over here. We can write this as the sum over K, sum over N, pk, and then we'll put this bra over here, A, and then we will insert a ket bra of n's, just like we have over here. This is the identity operator, because we're summing over all of the n's over here. And then we will finish off with psi k inside of this ket. So what we can see is we have a number and another number. This is an inner product over here. We can identify that these two terms in a ket bra, they are projectors, but we can also group this as an inner product over here, and this result is also a number. So whenever you have an operator that's sandwiched by a bra and a ket, you can think of this as a square matrix in the middle, and you can think of this as a column vector and a row vector. So you can sandwich this square matrix between a row and a column. And when you perform that matrix multiplication, you're going to get a numerical value. And then if you take all those numerical values and you scale them by probabilities and you add them up, you're going to get this expectation value over here. Now this over here is also a numerical value, and this is a numerical value. So that means we can use commutativity and we can swap the order. So let's swap the order. I'll write this as sum over n, sum over k of pk, and then we'll have n psi k, and then we'll connect this to this psi k over here. So then we have a ket bra combination of psi k, and then a is going to be here, and finally we have n. So you can see this combination is the same as this combination, and this combination that was on the right is now on the left. And now we can rearrange this. We can move this pk on the inside over here, and we can take this summation of k on the inside, and that's going to give us the sum over this index n, and then we're going to have a sandwich of bras and kets with the label n. So we're going to have the sum over k, pk, and then this ket bra combination of psi k, and then we're going to have a over here. So this is starting to look familiar. What we've done is we've just moved all of these k terms, all this stuff that involves k, inside of this sandwich. So now we have the same thing that we had up here. We have a sandwich of these basis states. And this outside over here, that is the trace. So we have the trace of this quantity times A. But what is this quantity? This quantity is the density operator. So we can write this as the trace of the density operator times A. So that is what this expectation value of A is equal to. You can take the trace of the density operator times A, and that will give you the expectation value. So now up here, I'm going to write what this rho is. So I'll write this explicitly. Rho can be expressed as the sum over some index k, pk, times this ket bra combination of psi k's. And we can also write this in the eigenbasis of rho. And I can denote that by the sum over j of lambda j times the ket bra of these j states. So it is possible to diagonalize this rho, and we can do that with the eigenbasis. We can find all the eigenvectors and the eigenvalues, and then we can apply a unitary transformation. We can sandwich this rho between u and u dagger, and then that unitary transformation will take us into this different basis. So this is the same operator, just expressed in a basis where the matrix representation is diagonal. And that is very convenient for computations. If you want to put this inside of some function, for example, if you want to take the logarithm of this row, which is used to define the von Neumann entropy, then it's very convenient to deal with this diagonalized version of rho. So that's what we have over here. This definition is the same as this definition over here. Notice that in the definition of rho, we're dealing with a ket bra. So these are projectors in a linear combination. Whereas in this definition of the expectation value, we're dealing with a bra ket sandwich. So this bra ket is swapped over and we have a ket bra sandwich. So that's related slightly to this idea of taking the trace of a ket bra. When you take the trace, you swap the ket bra and you turn it into a bra ket. You can loosely think of that as a related concept. I want to also demonstrate that we didn't have to insert the identity operator on the right. We could have inserted it on the left. And let's see what that would look like. We could have inserted this identity over here on this side of A. So I'll write this as the sum over K, sum over N, Pk, bra psi K, and then we can put the identity operator there. So we have this N ket bra, and then we have A, and then we have psi K as a ket. So now you can see that we have this combination on the left-hand side. And we can do the same thing. We can swap the order of these guys around, and that's going to give us the sum over N, the sum over K, Pk, and then we're going to have this quantity on the left. So we have N, A, psi K, and this psi K is going to connect up with this psi K in a ket-bra combination. And then finally we have this N. So now we can identify this as an inner product and this as a numerical value that results from evaluating matrix multiplication. We have a row, and then over here we have a column, and in the middle we have a square matrix. So now we can also identify this object here, and that's what's going to be used to construct the density operator. So let's move all of the things that involve K inside this sandwich. And that's going to give us the sum over N. Then we have bra N over here. And then we're going to have A. So A is on the left now. And then we have the sum over K of Pk. And then we have the ket bra combination over here. And then finally, we will close this sandwich. And this is the same as the trace of, what do we have? We have A and then rho. So that's A and then rho. So you can see that if you swap the order of these operators inside the trace, it doesn't matter. You can have A rho or you can have rho A. As long as you take the trace, you're going to get the same expectation value. So we've seen that you can insert the identity operator on the left or on the right. It doesn't make a difference. And this is one of those essential properties of the trace. Now, let's also take the trace of rho. So let's see what happens when we take the trace of rho. You can consider this as a special case if A is just the identity operator. So you can multiply this rho by the identity from the right or from the left over here. We have A and then rho. So what is that going to be? Well, we can use this definition and we can sandwich it in between these bras and kets. So that's going to give us the sum over N, sum over K of Pk, and N is going to come over here, and it's going to sandwich the ket bra of psi Ks, and here we also have an N. So we have a bra and a ket sandwiching them together. And then we can swap the order of these two. So that's going to give us the sum over, we can also swap these guys around, sum over K, sum over N, Pk, and then we're going to have psi K, and in the middle, we can link this N and this N, and that's going to give us a ket bra combination, and then we're going to have psi K over here, and now we can identify the identity operator. This is the resolution of the identity, just like we had up here, and we can get rid of this identity because it has no effect, and that's just going to give us the sum over K of Pk times this inner product of psi k with itself. But psi k, these guys are all normalized states. So because they're normalized states, the inner product of these states is going to be 1, and that means all of these terms are going to be 1. So we're just going to be left with the sum over k of all of the probabilities. And the probabilities, they have to add up to 1. That's going to give us 1 over here. So the trace of rho is equal to 1. This is analogous to the normalization condition for states. So just like we have this condition over here, this is equal to 1. The inner product of a normalized state with itself is equal to 1. The trace of the density operator is equal to 1. Now, let's have a look at another very important property of the density operator, which it is called positive semi-definiteness. So if we sandwich the density operator between some normalized state phi in this format, so we have a bra and a ket sandwich of the density operator. What is this going to give us? Well, we can again use this definition. We're going to have the sum over k, pk, then this bra is going to act from the left, and this is going to act from the right. So that's going to give us phi, and then we're going to have this psi k ket bra combination in the middle, and then phi again on the right. And we can identify this as an inner product, and this is an inner product. And the order is swapped over. That means it's the same as a complex conjugate. That's because the inner product satisfies conjugate symmetry. So we can write this as the sum over k of pk times the absolute value of the inner product of phi with psi k. And this is squared over here because we have 2 copies of this. So if you have a complex number times its complex conjugate, that's the same as the absolute value squared of that complex number. And the inner product evaluates to a complex number. So we have something that is non-negative. This is never going to be negative. It can be 0 and it can be a positive number. So that means it's non-negative. And probabilities are also non-negative. They can be 0, but they can never go below 0. So we have something that's non-negative times something that's non-negative, and then we're summing that together. That means the result over here is going to be something that is non-negative. It's greater than or equal to 0. So that is why this is called positive semi-definite. We have to say semi because there is the possibility that this could be equal to 0. And one property of positive semi-definite operators is that the eigenvalues are non-negative. So these eigenvalues up here in this diagonal form, they are all going to satisfy this property. So all of these lambdas, these eigenvalues of rho, they are non-negative. They can be 0, and that's why we have to say semi. So it is semi-definite, or positive semi-definite. That is a very essential property of the density operator. One more interesting thing I wanted to show you with this Dirac notation is what happens when we take the square of the density operator. So this is useful when we're computing the purity, which is defined as the trace of the density operator squared. So the rho squared over here, that is going to be equal to 2 copies of rho. And let's write it in terms of this diagonalized form, in the eigenbasis of rho. We're going to need 2 indices. So we're going to have the sum over J0, lambda J0, and then we're going to have the ket bra of these J0s. So that's what we've got in the first copy. So I'm just changing the index, I'm calling it J0. And then the other index I'm going to call J1. So we're going to have the sum over J1, lambda J1, and we're going to have J1 in a ket bra combination. And I'll close the bracket over here. So now what we can do is move some of these terms around. Every time we have a number, like a complex number or a real number, we can always shift them around. That's why we're allowed to move these pk's around in this line. And we're also allowed to move these lambdas around too. But we're not allowed to swap the order of things in Dirac notation unless they can be evaluated as complex numbers. So if you see inner products, you can swap them around. But if you see kets and bras and kets in general, and you can't actually condense them into something like an inner product or an identity operator, you're not allowed to swap them around. Commutativity is not guaranteed in quantum mechanics, but sometimes you are allowed to swap things around. And these are the special cases that we can use to manipulate algebraic expressions. So let's write this as one sum. We have the sum over J0, sum over J1 of lambda J0, lambda J1. So we're just moving this lambda over here. And then let's take this projector and this projector and smush them together. So that's going to give us J0 forming a ket bra, and then J1 forming a ket bra. And we can identify, because this is an orthonormal basis, we can identify this as an inner product. And this inner product can be expressed as the Kronecker delta. So this is the Kronecker delta of J0 and J1. So it is 0 if these indices are different, and it is 1 if the indices are the same. So if the indices are the same, we get 1 over here, and then we can move this and this together to form a ket bra. And in that case, J0 and J1 are equal to each other. We can just call that index J. So let's write this as the sum over J of lambda J squared, and then we have the ket bra over here. So now what we can do is we can take the trace of this. So I'll write this down here. The trace of rho squared is equal to the sum over J of these lambda J squared. So that is what this is equal to. And this can be used to compute the purity of the state. And you can see how it's very convenient to deal with the diagonal matrix, because if you apply some kind of function to this diagonal matrix, it's the same as applying to the function to each of the individual terms along the diagonal. So we just have to square each of those terms, and then we can sum that together, and that's going to give us the trace of rho squared. And this is the purity. And an interesting property of this quantity of the purity is that its lower bound is 1 over the dimension of the Hilbert space, and its upper bound is 1. And this is the special case where we're dealing with a pure state. So that's a purity of 1. And this over here is the special case where we're dealing with the maximally mixed state. And I'll write this as a less than or equal to sign because it can range between these values. So these are the extremes. And any value that's in between is just an arbitrary mixed state. And at this extreme, we're dealing with a pure state, which is a special case. And in this extreme, we're dealing with the maximally mixed state. So these were some interesting properties of the density operator. We saw how to compute expectation values, and we saw that the density operator is positive semi-definite. That means all of its eigenvalues are non-negative. They can be 0. That's why we have to say semi-definite. So this is less than or equal to. It's not a strict inequality. So that was the density operator. You can find more videos about this density operator in the quantum mechanics playlist.